All right, let's move into section 6 here, inferences about populations. And so we're going to talk a little bit about situations where we have an unknown standard deviation. Whenever we have an unknown standard deviation, we're not going to use our normal distribution. We are going to use a t-distribution. The shape is going to be very similar to a normal distribution, except for the tails will be a little bit fatter, and we'll see what that looks like here in a little bit. So if you remember, according to the central limit theorem, the sampling distribution of a statistic, like the sample mean, will follow a normal distribution as long as the sample size is sufficiently large and we know the population standard deviation. Therefore, when we know the standard deviation of the population, we can compute the z-score and use the normal distribution to evaluate the probabilities with the sample mean. But sample sizes are sometimes small, and we often do not know the standard deviation of the population. So therefore, we're trying to predict two of the variables. We're trying to figure out what the average is and the population standard deviation. We're using the sample average and the sample standard deviation to use those two things. So it would not be a normal distribution. We would move to a t statistic or a t score. Okay. A t distribution is very similar to a normal distribution. It has something called degrees of freedom. Degrees of freedom. We're going to explain that here in a little bit. But our degrees of freedom will be n minus 1. And again, the n minus 1 is because we lose 1 degree of freedom by using the sample mean as the estimate of the population mean, as well as the sample standard deviation, estimating that as the population standard deviation. Okay. So here's how it looks. A t-distribution, right, is out here. These blue lines, they've got the fatter tails. There's more occurrences of events happening out here than our standard distribution here in the purple is, okay? So our t-distribution out here in the blue will have different degrees of freedom. But you'll notice we get to 10 degrees of freedom. So degrees of freedom again was our n minus 1. So n is the number of observations. So as, for example, 10 degrees of freedom would be 11 minus 1 would be 10. The larger we get, we go up to 20 degrees of freedom. Eventually we start to approach our standard normal distribution, the more degrees of freedom we get. In essence, the larger the sample becomes, the closer we get to normal distribution. In essence, we're getting closer and closer to the population number itself. Okay, so the degrees of freedom refers to the number of independent observations in a data set. The number of independent pieces of information that go into estimating a parameter is the degrees of freedom. So in general, the degrees of freedom of an estimate of a parameter is equal to the number of independent scores that go into estimating it minus the number of parameters used as intermediate steps. So in this case, right, we're in our normal process, we're using the sample average to estimate the population average. Well, when we don't know the population standard deviation, now we're using a second one. Now we're using a second one. So we need to do that n minus 1. So let me think of it another way. Let's say that you have four numbers. You have four numbers A, B, C, and D. Okay, and those all must add up to be a fifth number. We'll call that fifth number T, the total. Okay, so those four numbers A, B, C, and D must add up to be T. You're free to choose those first four numbers. I pick whatever numbers you want, right? But I need that fourth number to, in essence, make sure that you add up to be T. I can make that fourth number whatever I need it to be, depending upon what those first three are, so that n minus 1 gives me that degrees of freedom, right? So it's, in that case, my total T minus 1, right, would be able to, I'd be able to pick out that fourth number and figure out what that degrees of freedom would be, okay? Here's a table, an excerpt from a table, but you'll see, just as we saw on the distribution chart here with our curve, right? The closer we get, the higher number of degrees of freedoms we get to. Anything above 100, kind of approaching infinity, we actually get back to our normal distribution. Our curve becomes tighter and tighter together. Our tails become smaller and smaller. And all of a sudden, we look very similar to our normal distribution. As a matter of fact, these numbers should look familiar to it at 1.645, 1.96, and on and on. Okay. Okay, so whenever we are using our t-distribution, it's going to be very similar when we're trying to figure out our interval estimate or our margin of error. It's going to be very similar to what we did with our z-distribution, except for we're going to substitute in the z for t and t for z. And then also we're going to have S up here, which is going to indicate our sample standard deviation versus our sigma, which is the population standard deviation. Okay. In the real world, the population standard deviation is rarely known. Sometimes you run into situations where you have studied a population so many times and the population standard deviation has come out relatively close to it that you can estimate the population standard deviation. But in reality, we'll almost never know the true population standard deviation. Okay. All right. And so let's work a problem. I think this will help to kind of see how this works. So let's say a reporter for a student newspaper is writing an article on the cost of off-campus housing. A sample of 16 efficiency apartments within a half mile of the campus resulted in a sample mean of 750 per month and a sample standard deviations of $55. Let's provide a 95% confidence interval estimate of the mean rent per month for the population of the efficient apartments within half mile of campus, and we'll assume that the population is normally distributed. So what information do we have? Well, we have a sample standard deviation. We do not have a population standard deviation, so we know that we'll be using our t-distribution. We have a sample average, an x bar, 95% confidence interval estimate, and we know our n. We took a sample of 16. Okay, so the first thing we do is we would go to a statistics table, a t-distribution table, and we would look at 95% confidence. And again, it's alpha divided by 2. Alpha is 0.05 divided by 2 because it could be in the upper tail or lower tail. So we're going to take that by 2. So 0.05 divided by 2 is 0.25. The area in the upper tail. And we are looking at 15 degrees of freedom, or n. Our n was 16 minus 1. So we will get to 15 degrees of freedom. And we know right there our t value is 2.131. Okay, and all this happens in a table. Some calculators can do this, but again, you would look up a t-distribution table and you walk through this process. Okay, so from that information, we simply go back to our formula and plug it in. Well, we know the t alpha divided by 2, which is t at 0.025, we found was 2.13. Our sample standard deviation was 55. Our n was 16, and we simply plug in the numbers and work the math. So 750 was our average, and our interval estimate would be 750 plus or minus the 2930. 2930, this whole equation here, just a reminder, that is our margin of error. That's what we did in our last video. Okay, so our interval estimate of the rents for apartments within a half mile of campus would be $720.70 and all the way up to $779.30. Okay, $779.30. All right. So, a couple of things about the unknown population standard deviation. Again, this is kind of going back to some of the concepts within central limit theorem. Again, 50 sample sizes is always going to be the gold standard for you. That is going to be the minimum amount. There are some other ones in here, when we can use 15 if it's symmetrical or we believe it's not highly skewed, we can go as small as 15. I would never, ever encourage you to do that. You have to justify why you're doing that and prove this out versus saying, hey, let's just go grab 50 and everybody should be happy after that. Okay. So as a little flow chart here, we're just going to look at can the population standard deviation be assumed to be known? If yes, we'll use our z value. If no, we'll use our sample standard deviation and we'll use our t value here. Okay. And again, the way we find the t is with our degrees of freedom, n minus 1. N minus 1. All right. Let's say that we wanted to figure out what if we knew our margin of error? Hey, we want a margin of error of $10 or $5. Well, we could use that number and then go out and figure what ends or the sample size, the number of observations that we would need. We could figure it out from there. Okay. So what we'd simply do is we'd simply rearrange our formula. We'd come in here and say, okay, if we knew our margin of error, this is equal to the margin of error, we can rearrange this formula to solve for n. we can figure out what the sample size needs to be in order to hit that specific margin of error. All right. A couple of things are important here in that in the necessary sample size equation requires a value for the population standard deviation to be estimated. So a couple of things. We're just going to put in a planning value. We can use our best judgment. If we've got some pilot study information, we could use that as well. The best guess or best estimator of what that could be from other studies. So we can use some of that information as a planning value. Okay, so again, if we go back here to our formula, we can see, hey, in order to work this formula here, we've got to have our population standard deviation. If we're not sure what this is, we can come down here to one of these three techniques, use a previous study, do a pilot, or use our best judgment. All of these must be justified, by the way. Okay. Let's work a little sample. If you guys remember our discount sounds where we were working through a retail shop, we're trying to find a new location. Suppose that the discount sounds management team wants an estimate of the population mean, right there, income, such that there is a 0.95% probability the sampling error is $500 or less. Ooh, so now we know that our margin of error must be $500 or less. So how many individuals do we need to sample at this point, right? So at that point, we are looking at solving for our n. We know that E is 500. Our confidence is 95%, which is equivalent to a z-score of 1.96. Okay. So based upon that information, we're rearranging our formula here. We're simply plugging this in. The 1.96 squared times the 4,500 squared divided by 500 squared. Right? So we would come out, we need to take a sample size of 311.17. We rounded up 312 in order to get a margin of error of $500. Okay, we are 95% confident that the margin of error is within $500. Okay, so it's a different way to work backwards. And this is really helpful a lot of times when people need to understand, hey, I need you to be more confident than you are, right? So if we need to be more confident, if we think about this, 95%, I need you to be 99%. Well, this number is going to shoot up here. This is going to make this much larger. We'd have to sample more people in order to ensure that we are 99% confident. Okay. All right. Okay, population proportion. A population proportion is going to act very similar to our sample proportions that we have. Again, remember population proportion is just saying, yeses and nos. It's either going to fit into one or two categories. Men and women, what proportion are women? What proportion have taken this training? What proportion of our employees have a bachelor's degree, right? It's a checkbox, a yes or a no, okay? Within proportions, we are always using our z-score. Why is that? Because, now we're using a sample proportion, and there is no population standard deviation that we're concerned about in our formula. Okay, so it's always going to be our z distribution. The t-test or the t-distribution is never used in population proportion. That's something to keep in mind. Just a reminder here very quickly, the n is equal to our sample size and the p is the sample proportion, okay? So here's our formula to do our interval estimate. Again, looking at the population proportion plus or minus z alpha divided by 2. And again, all of these are broken down where the p bar is the sample proportion, the z alpha divided by 2 is the value in the upper tail. And then here again, we've got our 1 minus alpha as our confidence interval. So whatever our proportion turns out to be, again, we're going to take 1 minus that in order to square root that in our equation. Let's do a sample problem, and I hope it'll make things clear for you. So let's say our Political Science Incorporated, PSI, specializes in voter polls and surveys designed to keep political office seekers informed of their position in a race. Using telephone surveys, PSI interviewers asked registered voters who they would vote for if the election were held today. So in a current election campaign, PSI has just found that 220 registered voters out of 500 contacted favor a particular candidate. PSI wants to develop a 95% confidence interval estimate for the proportion of the population of registered voters that favor that particular candidate. Well, In this case, we need to figure out what our P bar is, which is our sample proportion. And the way that we do that is we simply take our um, X, the number of registered voters who said, yes, I'd vote for them, divided by our N. Okay, and so in this case, we take 220 divided by 500, we would get 0.44. 44% favor a particular candidate. So what we'd like to figure out here, right, is a confidence interval based upon that proportion. At 95%, our z-score is going to be 1.96. And so we're simply going to plug in our information into our calculations here. We've got 1.96, the alpha divided by 2. We found that 0.44 times 1 minus 0.4 over 500 square root is equal to 0.0435. So what does this mean? This means that we are 95% confident that if the election were held today, that the proportion of voters that would favor the candidate would be between 39.65% and 48% of the population would vote for you. Again, if you need a majority, this isn't going to cut it. So now we know where to focus, right? We know where to focus our efforts. And so we want to be sure of that. And again, we would fully expect we would go from 95%, but as we get closer and closer to the actual election, we would expect it to move up to 99%. We'd want to contact more registered voters. We want to understand where we are in the polls and move from there. Okay. All right, we can do the exact same thing that we did with our sample average to figure out the proportion, and we can figure out our n. We could rearrange the equation and solve for n just like we did in the past, okay? When we only know what the proportion of the sample is after we've selected the sample, hopefully that makes sense. We only know what this proportion is after we've actually selected the sample. So before, if we go back to our example up here, we took a sample, we contacted 500 people, and we got to a 44% of people would vote for him. This equation down here says, hey, in order to find your N, you've already had to contact those 500 people. Well, how do we do that? We can add some sort of planning value into our equation, okay? We can add some sort of planning value, this P star. So if we've done a election in the past, for example, we would use the most recent proportions as our planning value and go from there. Or we could use our best judgment. Otherwise, the most conservative is always 50-50. The most conservative value you'll ever get is always 50-50. That will lead to the highest value of n that you can achieve. Okay, so kind of keep that in mind. So again, we went through the interval estimates. We figured out how to understand how many people we need to contact in this process in order to make sure that our margin of error is being achieved. And so hopefully that makes sense. And this does bring us to the end of this section.